The existence of an infimum is something that needs to be proven. While we have an axiom for the existence of supremum, we need to prove the existence of an infimum. The reason why is because it's not very difficult, and making an axiom for it would simply just be a foolish mistake. It would just make the whole theorem look a bit weaker, and why not do it? It's a proof that's not too difficult, but it is a proof that are extraordinary difficult. At least they were for me when I transitioned from high school math to college math. It was a big shell shock. So let's go over it. It has a pretty clever idea, and then it follows kind of a linear path. So let's get right into the clever idea. It comes like right from the start, which is good. You do not need to keep it in mind and make a setup. You can just do that immediately. So we're gonna do it. So let's create a set we'll call minus m that has all the numbers from m but multiplied by minus 1. So for example, if m is a set that's 1, 2, then minus m is going to be minus 1, minus 2. Pretty simple, nothing too crazy, but that's the trick. It's something that you probably wouldn't do because it's not exactly something that comes to your mind, but with the knowledge that we have an axiom for the supremum, this may be something that you can figure out, which is very important, something that you should learn, because it's not very handy to actually remember these proofs, because your head would explode. It's much better to just remember the key ideas and study mathematics, and the rest will basically with good idea of the theory of that subject, you probably should be able to complete the proof. So this is the idea. Now let's do something that I had trouble with a lot, which is realizing that we can actually find the lower bound. It sounds silly, but I, for the life of me, couldn't figure out what I actually can and what I actually cannot do with proofs. Since then, I've come some way, not a long way, but some way, and I can somewhat realize that what are my limits in a proof and what are not. So I know that we can actually basically say this. Let A be the lower bound of m. I'm saying the, also this is the real number. It's pretty good to specify it. That's why I'm doing it. I'm saying the lower bound because I want to imply that, I actually mean the lower bound that's in, the sentence itself. So that's why I write it there. Now, what does it mean to be a lower bound? Well, for all x that are in the set M, a is smaller or equal to that x. That's the definition. You need to go to your classes to know that. It's not a very difficult or counterintuitive definition. It's pretty straightforward. But what does this imply? Well, it implies that minus a is greater or equal to all minus x. We just multiply this inequality by minus 1. Again, something we can do because it does not hurt the inequality. Everything that was the solution before, the solution still applies. Again, something that I had trouble realizing, what I can do in a proof and what I cannot. What does this imply? Well, this sentence says, actually this sentence is mathematically a bit wrong. I'm just gonna move it and write it there. Now it is correct. Well, what does this say? Well, it says that since for every x in M, a is smaller or equal to it, then for every x that's in the set M, minus a is greater or equal to minus x, right? But what does it actually mean? Well, we have a set that has all of these negatives, right? So what we can say is that we can say that therefore minus a is a upper bound. Should be a space here, should it? An upper bound of minus m. So there you go. That's again, that's something that you can just derive. It's not something insane. But now we're gonna use the axiom again. Another small clever idea, but we're already going into this proof with the knowledge that we're gonna use it, so we're gonna be using it now. And the axiom states that if a set has an upper bound, then it has a supremum. So again, as we've said before, if we can say that something exists, we can find it most of the time. In this case, definitely. And we're gonna do just that. So we're gonna say, let, for example, B. Let B equal to be a supremum of M, right? Let B be the supremum of M, and we actually, let's rename this. Let's go straight forward to the end, and let's just not call it B, and let's call it minus G. Why am I calling it minus G? Because then we're gonna make an assumption, another clever assumption. Well, okay, let's why are we making that assumption? Okay, let's think about it. So pretty trivially, something that we can all imagine in our heads. Well, since this is like the supremum of the negative set, then it's probably the infimum of the the positive set. Well, I'm saying positive, but it can have negative numbers that then flip into positives. But I hope we know what I mean. But it's something that can be easily imagined, but we need to prove it. That's math for you. So how do we prove it? We'll be proving by contradiction, basically, right? We will be proving by contradiction. It's pretty simple. Now, let's list what we need to actually prove. We need to prove two things. We need to prove the definition. Well, that minus G fits the definition of an infimum, and what the definition is. What do we need to prove? Well, we need to prove first minus G is a lower bound of M. That's the first thing we need to prove. And the second thing we need to prove is that for every big G that's bigger than minus G. I'm sorry, I am writing minus G, but I mean G. So for every G that is bigger than our small g, right? For every single one of these, it means that there exists some x in the set of M for which that x is actually smaller than it. What does it mean? It just basically means that if we find a bigger lower bound, then that lower bound is if you find another lower bound that's like bigger than our small g, then it's not a lower bound anymore, because we can find some x in set M that is bigger, smaller than it. Sorry, smaller than it, because that's why it is not a lower bound, basically. So let's go do it one by one. Let's prove the first thing. We're gonna be proving by contradiction. Assume G is not a lower bound of M. Then there must exist some x in M for which the x is bigger, smaller than G, right? Well, if that x exists, then the negative of that x belongs in minus m, and also this negative of that x is bigger than minus g, which immediately is a contradiction. Why is that a contradiction? Because we have defined minus g as a supremum for minus m, and for the supremum, the definition of supremum states that it's bigger than every single it's bigger or equal to every single number that is in its set, right? But this thing right here says that we can find one that's actually bigger than it, and that's a contradiction. So therefore our assumption is wrong, and it proves then it proves that g in fact is a lower bound of m. Now let's prove the other half, which is that if we can find a number that's bigger than g, right, which we can obviously. Actually, saying obviously in mathematics is not exactly great, but for our sake, let's just say it's pretty obvious that we can find a bigger number. If we can find for every single bigger number than our g, we can find an x in m that's smaller than it, right? So let's assume that that is not true. Let's assume that we have found a number that's bigger than small g, and we cannot find an x that's smaller than it. So assume that, let's just say g, assume that g, that's a real number, is bigger than small g, right? Fits, and it fits this criterion that for every x that is in m, it states that g is smaller or equal to that x, right? That's because that's the negation, right? That we cannot find an x that's actually bigger, right? Because we are assuming a contradiction. Hence, the name, proved by contradiction. Well, okay, so we can do the same old trick again. Well, then it means that minus x is smaller than g. You can find minus x is small. We for every single x, every x that is in m means that minus x is smaller. I'm sorry, hold on. For every minus x is smaller or equal to minus g, right? I'm just gonna rewrite this. Minus g, and also since we have this definition right here, by definition we can also state that minus g is smaller than minus g, right? So what does this combined say? Well, if we combine this together, we're saying two things. First, we have found a number that's smaller than minus g. That's number one. And number two, right? For every x that's in m, minus x is smaller or equal to than minus g. We can rewrite this as for every m that's in minus m, m is smaller or equal to minus g, right? Which, if you look at this, this is a clear contradiction to minus g being the supremum of minus m. So it is a contradiction. Minus g must be the supremum of minus m. Therefore, g fits this criteria. Sorry, I wrote this poorly. For every g that is bigger than g, there exists an x in m such as g is bigger. There we go. So it fits this criteria. Therefore, g must be an infimum of the set M. And since we haven't used a single number, we basically let our opponents choose whatever values they want to. We have proven this for every single set that has a lower bound and is non-empty. The set actually needs to be non-empty. The reason why it needs to be non-empty is because when we are creating the minus set over here up top, right around here, there we go. The reason why the set needs to be non-empty is because we are assuming that the lower bound, respectively the upper bound of minus m, we are assuming that it's bigger than everything that's in the set. But if there's nothing in the set, we cannot make that assumption. That's why we need to assume that something is in the set. So that's why it's, in the assumption. It's something that I probably should have mentioned earlier, but this is my 5th take of this proof. If I will ever do any more, I will try to make them shorter and make them less accessible. That's not the aim, that's the byproduct of them being shorter. Yeah, but I think this shouldn't really be, I highly doubt someone who's not too serious about math is gonna come here and watch me prove something. So I assume that if anyone watches this video, they're more likely to like math and know what's happening. So I'm gonna be doing that. It's also simpler for my throat because English is not my native language and it's rather difficult to keep it up for 20 minutes. All right, that's about it.